Okay, so if you're back for part 2, sorry about that. Apparently my pen died and that's why it wasn't working. I was wondering. So keeping up with this question, we ended off with number 35, and we were just talking about that to be in a conjugate acid or base, you have to be the difference of just one hydrogen. So number 1 and 3 would be just the difference of one hydrogen, so that could work. And then to be amphiprotic, you're either water or you are a compound that can act like an acid, so it has an H to donate, and you have a negative charge, so you can also act like a base. So to show that, that is 2 or 3. So it looks like our answer here is D. Now moving on from this one is about indicators, and as last video, I'm having trouble flipping into my data booklet. So with my data booklet, what I would want to look up is that information about chlorophenyl red. And this one has a indicator that will change between 5.2 to 6.8. If it is around 5.2, or I meant lower than that, it's going to be yellow. And if it's 6.8 above, it will be red. So this first part is giving you some information. So the first one, you just have the one compound. When it's tested, because it is an acid, it's in between the 5.2 and 6.8 color. It's giving you that orange color. And then the second one is a buffer system. That's what we want to recognize, because you have an acid and a base. You have a difference of one hydrogen, and we have the same starting information. Now, if you had these two and you add in more acid, how would it change? So for the first one, if you add in more acid, just because it's not a buffer system, it would have a lower pH, so it would go lower and your color would become more yellow. So that looks like it's going to be C. In solution 2, if you add it in, because it's a buffer system, buffer systems can resist the change of pH. So it would stay in between the 6.6 range and nothing else would happen. So the only thing that shows that is going to be C, and that will be our answer. Moving on from here, just a few more. This one we have some information about a reaction, and then it's given us a Kb and asking what is the Ka. So the relationship between Ka and Kb is this: if you multiply them together, it equals Kw. So if you want one and you have the other, you can divide Kw by, in this case, Kb, and we'll have Ka. So we'll have Kw divided by Kb, so 1.0, and if you don't remember this value, it's in your data booklet on page 89, and we're going to divide that by 5.8 times 10 to the negative 10. And once we've done that, just make sure you're keeping your denominator when you're dividing in brackets. You'll get 1.7 times 10 to the negative 5. And to fill this in, it'd be 1, 7, and 5. Now, moving over here, the amount of sorbic acid, which is this here, could be increased by. So this is showing again Le Chat. So this first one, adding HCl, that is going to be our answer. And the reason why, and we can rule out the rest, like if we add in NaOH, you'd be adding an OH, you'd shift to the left, making less of the absorbic acid. If you remove H2O, if you take out, you shift towards what you're taking out. It will take less, and same thing with this last one. Take it out, we're going to be shifting away. So HCl, we don't see H positive or Cl negative added directly in. So instead, we want to remember how it can react to take it out. And hydrogen likes to react with the OH ion and add them together to form water. And that would no longer be in our system because it's liquid water. So we would actually, by adding in HCl, would be removing OH from the system because it's going to form water. So with that removal, you're going to shift to the right, making more products, and you'd increase your absorbic acid. This part over here, asking which one would be favored. Here, if you're going to favor reactants, when you look at your acids page, page 8, 9, if your acid is higher than your base, your products are favored. If your base is higher up than your acid, your reactants are favored. So if you want reactants to be favored, you want your base to be higher than your acid. So in that case, just in terms of placement, you can place this on the data book, in the data booklet as the base, and you're looking for an acid below it. And the one that works out is C2H5COOH. So again, looking for one below because it would have a lower value. And what I mean by the placement, based on this Ka value that you've calculated, you would know where this reaction would go in on your data booklet. All right, so almost done here. I'm going the wrong way. Here, going back to a few organic questions, with this one saying how it's classified. The difference between saturated and unsaturated. Saturated means you only have single bonds. So we're seeing double bonds, that makes it unsaturated. Now about the rate of the reaction, I actually found this one a little bit confusing, and I went with fast, and I have to admit I did guess that, and I need to go look more into it, and there must be something I've missed. And I've been doing chem for a while, so I'm not sure. But I do know double bonds are really easy to break, and so for that reason, I would think that this equation could react quickly. Now, that's what made me pick it. But without any other information, I'm not sure where we would go for this. So just with this one, double bonds, easy to break, we'd have that reaction happening fast. This next one, nope, my dog's about to bark. Compound 1 can be produced from sorbic acid. So compound 1 is just missing a double bond. So breaking a double bond would be an addition reaction. And then the information of compound 2 can be produced from sorbic acid and blank. So compound 2, we're not breaking a double bond, but we are removing this H at the end, and that shows esterification. So this is A. Getting towards the end, I keep saying that, but we are almost there. So this one here, we have this information, and it's just asking what are our Bronston and Lowry acids. So what's acting like an acid? And in this case, we see water is losing a hydrogen. So that would be an acid on the reactant side. And on the product side, this big compound here, this hydrogen ends up going to the OH to form water. So the two that are acting like an acid would be B. And then, nope, no bark. And then this last couple here, for number 42, it's asking about the OH concentration. So we can use the formula Kb is your concentration of the hydroxide ion squared divided by the concentration of your weak base minus the concentration of the hydroxide ion. So what we should learn, because this is derived from ice, if you know the concentration of a hydroxide, you use it. If you don't, you could ignore it in the denominator to find it. So now we can fill in that information. We have the Kb value, 1.62 times 10 to the negative 6. This is going to equal your hydroxide squared, sorry, that's 2, divided by the concentration of your weak base. So now you're just solving. So you want to multiply up and then square root. And if you do this correctly, you will get B. So multiply this out of the denominator and then square root the whole thing to get OH by itself. Okay. Now, this one here, giving information about some compounds with their Kas, and then asking which species is both polyprotic and amphiprotic. So to be polyprotic and amphiprotic, you have to have more than one hydrogen or more than one negative to donate. And to be amphiprotic, you're able to act like an acid or a base. So with this, actually, 2 or 3 work. Okay, so we have, in this case, more than one hydrogen, and in this case, more than one negative to be an acid or a base. And then in here, you do have hydrogens to donate and negatives. Now, this is also showing that you understand that your acidic hydrogen is coming from the COOH. So these hydrogens are not acidic, so the ones I'm looking at are part of that COOH part. Now, the species that is a conjugate base, if you're a conjugate base, right, you have gained a hydrogen. So here, I just want to go, I'm sorry, the species that is the conjugate base of if you're the conjugate base, you are getting a hydrogen from this compound. So this one would be 3. The species with the weakest conjugate base would be number 1. And the species that will form a buffer when mixed with this here would be number 2, because that's the difference of 1 hydrogen. Okay, now over here we have some information, and then it says the equation that represents the reaction of hydronium with your buffer system is blank, and the effect on the buffer to the pH. So the point of the buffer is to maintain the pH. So we're not looking to decrease it or increase it. And if you're adding in hydronium, you would want to react with the base part of the buffer because this is an acid. So the reaction that shows that is A. Okay. And this one here is showing that we understand, and this is actually more like Chem 20, but that's okay because don't overthink it. We don't have a weak acid or a weak base, so we don't need to use Ka. It's just asking about the concentration of hydroxide, but you're given the pH. So we would need to turn your pH into pOH, and then when you have the pOH, you can get the concentration by taking the negative log. So let's do that quickly. Do 14 minus 5.40. And I had most of this written down, but of course I don't have it for this one. And also I can't do it in my head under pressure. So we get 8.6. So that's your pOH. Concentration of hydroxide will equal 10 to the negative 8.6. And when you do that, you'll get 2.51 times 10 to the negative 9. So your answer here is 2, 5, 1, and 9. And now this very last one is about your titration. So this is just showing your titration curve. What you want to remember is that this part here is in your Erlenmeyer flask. Whatever you're adding in, that was in your burette. Right? So that would be the part that comes up here. That's what we're adding in. So if your starting pH is closer to 12, we know that you're starting with a base. And if your ending pH is closer to 0 or 1, you know that you were titrating with an acid. So the first part saying the titrant that is added, that would have to be an acid. And then because you have this one equivalence point and this second equivalence point means that you had something that could react again, and that means you're polyprotic, not monoproduct. So that would be D. So as always, again, if I've made it this far, thank you so much for watching. If you are doing the diploma on Tuesday, best of luck to you. If there's anything else I can help with you with, just let me know and I'd be more than happy to. Thank you for watching. And if this is helpful, please subscribe. Thanks again.